Here we go with chapter 4.4. We are looking at limits at infinity today. So prior to this lesson, we've learned how to sketch curves that are polynomials or root functions. And where we're going next with this is we're going to graph rational functions. But before we do that, we need to understand how to find limits at infinity. So this first question is grabbing limits off of a graph. You'll remember this from earlier in our course. So the limit as x approaches -1, and it doesn't specify from the right or from the left, so we're looking at from both sides, and from both sides it is approaching infinity. The limit as x approaches 2, so I see that it's approaching infinity on one side, negative infinity on the other side, so that would be a does not exist. The limit as x approaches infinity, now we did not do this earlier in the course, so as x approaches infinity means as this graph continues on to the right. And so follow the pattern or the behavior of the graph, and you can see that this graph is flattening out. It's getting closer and closer and closer to this y value of 4. And it almost looks like this might have a horizontal asymptote at 4. So the limit as x approaches infinity is 4. The limit as x approaches negative infinity, now we're looking at left side behavior, and this looks like it is flattening out at 2. So there's a different asymptote for the left side. There's a horizontal asymptote at +2. Okay, so right beside that example, you'll see in the box the several limits as x approaches infinity that we are going to use kind of as the foundation for the rest of the limits that we find algebraically here. And so the first question says, find the limit as x approaches infinity of 1 over x. Now we know from our previous study of limits that when we try to evaluate a limit, the first thing we try to do is substitute an infinity in. But we can't really evaluate a number that is 1 over infinity. However, let's consider the idea of what's happening here. This denominator is getting very, very, very large. When I say large, we're going from maybe 1/10 to 1/100th to 1/1000th, and so on and so on and so on. And as that denominator gets really big and approaches infinity, what is our fraction as a value getting closer and closer to? It's getting closer and closer to 0. So the limit of 1 over x is actually going to be 0. And if we were finding the limit as x approaches negative infinity, that would just mean my numbers in the denominator are negative. But 1 over negative 100,000 is still a value that is getting closer and closer and closer to 0. So if you look at the more general form of this limit, what if instead of having a 1 on top, I made it any kind of constant? For example, I could put a 13 on top. And what if instead of just an x on the bottom, I added a power to it? So maybe my power was 5. How will that change the behavior of our value of this expression? Well, I still have a denominator that is getting very, very large. Whether it is positive or negative, it's getting very large. And the larger the denominator, the closer this value of that fraction gets to 0. So any constant number over any variable to a power is going to approach 0, whether I'm talking about a positive denominator or a negative denominator. So all of those limits are equivalent to 0. Okay, so when we look at rational functions and we are being asked to find limits as x approaches infinity, I'm going to show you a fast way to answer this question if you needed to show no work at all, and then I'm going to show you an algebraic way to work these questions in case you had to show supporting work. if given the choice, I would always choose the faster version, but if you are an IB student, you don't always have that choice. And if you're an AP student, you don't always have that choice. It depends on the nature of the question you're working. So you might recall this from Algebra 2. So we are looking for the limits at infinity, and we know from this graphic example that if there is a horizontal asymptote, that helps us determine what the end behavior is. So there are three scenarios we're going to consider when identifying a horizontal asymptote. If our numerator's degree and our denominator's degree is exponent, if those degrees are the same, so if we look at this example, x cubed over x cubed, they are the same power, we are going to grab the quotient of the coefficients. So we take that highest power term we're always looking at. The powers are the same. You are going to grab 7 over 8. And our horizontal asymptote is at 7/8. So if they ask you to find the limit as x approaches infinity or negative infinity, the answer would be 7/8. If the numerator is greater than the degree of the denominator, so look at our highest power terms, the first two terms. This numerator has a power of 6. The denominator has a power of 3. Those are the degrees. So when the numerator has a greater degree, it means there is no horizontal asymptote. Now that does not mean it doesn't have a behavior. It means the behavior doesn't hone in on a number. More than likely, the limit is probably approaching infinity or negative infinity, but we'll look at that later. So that would be none. And then the last scenario is if the degree of your numerator is smaller than the degree of your denominator, as in this example where you can see we have an x squared on top and an x cubed on the bottom. And when the denominator is a bigger degree, our limit approaches 0. This is actually a simpler example of that. That is absolutely a fraction where the denominator's degree is bigger than the numerator's, and there's my limit as x approaches infinity of 0. Okay, so we're going to take a look at these three examples underneath, and we're just going to first find the limit graphically, but when I say graphically, we're not going to sketch it. We're just going to envision where the horizontal asymptote is, because that will tell us the limit as x approaches infinity. So if I were to compare my degrees, that's what we're doing, is comparing the degrees, like these scenarios A, B, and C. This first scenario, x cubed over x cubed. When the powers are the same, that's this first scenario here, we grab the coefficients of those leading terms. So I'm going to grab this 8 and that 2. So my horizontal asymptote is going to be y equals 8 over 2 or y equals 4. Let's jump to the example number 3. We have a denominator that has a greater degree than the numerator. So when our denominator has a greater degree than the numerator, that's this last one, we are looking for a horizontal asymptote at y equals 0. And for this third scenario, our numerator has a greater degree. So our numerator has a greater degree, so we have no horizontal asymptote. That doesn't mean there isn't a behavior. As the limit approaches infinity or negative infinity, we're just going to have to do a little bit more work to find it. Okay, so that's the fast way of getting these answers. You can answer it literally in 10 seconds or less. But if you were asked to show some supporting work, what we're going to do is we are going to divide every single term by the highest power variable, and then we're going to evaluate. What do I mean by that? So if you look at this expression here, my highest power of my variable is x cubed. So I'm going to divide every single term by x cubed. So here's what this is going to look like. We're going to have 8x cubed divided by x cubed plus 5x squared divided by x cubed plus 3x divided by x cubed. And then we're going to divide all of these denominator terms by x cubed as well. So we would have 2x cubed divided by x cubed plus 6x squared divided by x cubed minus 9 divided by x cubed. And I'm going to clean that up. So this first term would simplify to 8. My second term would be simplified to 5 over x. So two of my x's on top simplify with 1 on the bottom. And for this last term, I'd be left with 3 over x squared. In the denominator, first term simplifies to 2, 6 over x minus 9 over x cubed. And I forgot to carry my limit notation over, shame on me. Envision that I also carried that limit notation over here. And I want you to imagine that we substituted an infinity in, because remember, with all limits, we eventually want to substitute in. And if I substitute an infinity into my first term, I'm going to get 8. If I substitute infinity into my second term, 5 over infinity, that is an example like my limit up at the top. It is a constant number over a variable to a power. And so I know that this 5 over x is really going to approach 0. So my limit is 0. Look at my next term, 3 over x squared, a constant over a variable to a power. Same deal. This is going to approach 0. On the bottom, we'll carry over that 2. 6 over x is going to approach 0. And 9 over x cubed is going to approach 0. So what's happening here is this simplifies all the way to 8 over 2, which is 4, which matches the same answer we got when we just compared the numerator of the fraction with the denominator of the fraction and grabbed their coefficients. So you've now seen the fast way by identifying the horizontal asymptote, and you've now seen the algebraic way. Let's look at another example. Let's look at example number 3. So we're going to solve this algebraically, and we're going to divide all of these terms by the highest power in the denominator. The highest power. So the highest power in the denominator is x to the 4th. So we're going to take 3x and divide by x to the 4th. We're going to take 5 divided by x to the 4th. On the bottom, 6x to the 4th over x to the 4th plus 3x over x to the 4th plus 3 over x to the 4th. And for my first term, that is going to simplify to 3 over x cubed. And I'll just carry over that 5 over x cubed, x to the 4th. On the bottom, this will simplify to 6 plus 3 over x cubed plus 3 over x to the 4th. And as you substitute infinity in, anything that has a variable on the bottom is going to approach 0, and a constant on top is going to approach 0. So all 4 of these are approaching 0. So what am I left with? 0 plus 0 over 6 plus 0 plus 0, which is 0. And that matches the horizontal asymptote that we detected. Okay, if you take a look at example number 4, we're going to do the same exact thing. We're going to divide by the highest power. And so we'll have 6x cubed over x cubed minus 2x over x cubed plus 1 over x cubed over 3x over x cubed plus 1 over x cubed. Now remember, this was a scenario where we had no horizontal asymptote. So let's see how this looks different. So 6x cubed over x cubed is 6 minus 2 over x squared plus 1 over x cubed. In the denominator, 3 over x squared plus 1 over x cubed. And all of those fractions with variables on the bottom approach 0. So that leaves me with 6 minus 0 plus 0 over 0 plus 0, which is 6 over 0, which is actually undefined, which means you cannot evaluate this algebraically using this technique up here. But I am going to show you a better way. So when I approach these problems, I always find the answer first just by identifying the horizontal asymptote. And if I see it's the scenario where there isn't a horizontal asymptote, I don't actually go through this process. What I do instead is I long divide this expression. We did this back in Algebra 2 when you learned how to use synthetic division and long division. And so what we're going to do is long divide this polynomial over a polynomial. So I'm going to squeeze this in over here. So we're going to have 6x cubed minus 2x plus 1 divided by 3x plus 1. So I know I'm going back a couple years. When you long divide, you ask yourself, what do I have to multiply 3x by to turn it into 6x cubed? We would have to multiply by 2x squared. And now I would multiply both of these by 2x squared. So 2x squared times 3x is 6x cubed plus 2x squared. And now we subtract both of these terms. So my first terms cancel, and I'm left with, now be careful, we have, these two terms are not like terms. So you want to make sure you don't combine those. So you would have negative 2x squared minus 2x plus 1. And then you're looking for, what do I have to multiply 3x by to turn it into a negative 2x squared? No, that's not quite as pretty. So instead of figuring out what you have to multiply this by to get this, you can also just divide. Like up here, I could have said, what's 6x cubed divided by 3x, 2x squared? So if I took negative 2x squared divided by 3x, I would have negative 2/3 x. And that's what I'm going to multiply both of these by. So negative 2/3 x times 3x is going to leave me with negative 2x squared minus 2/3 x. And now I'm going to subtract both of these. So subtracting makes this become a positive and makes that become a positive. My first term cancels. Negative 2x plus 2/3 x is going to leave me with negative 1 1/3, which is negative 4/3. Okay. And then we'll carry down our plus 1. And then one last step, we would divide negative 4/3 x by 3x. And so if that's hard for you to do in your head, negative 4/3 divided by 3 is the same as negative 4/3 times 3 over 1. I'm sorry, times 1 over 3 times the reciprocal. So you would get negative 4/9. So we would have a minus 4/9 up here. And now I multiply. So negative 4/9 times 3x is going to leave you with negative 4/3 x minus 4/9. Subtract, subtract. So those become a positive. 1 plus 4/9, so 1 and 4/9, which is 13/9. Now you might be thinking, oh my goodness, will we have to do this every time? And nope. I wanted to show you one full example of long division, but you will be very pleased to know that when I work these problems in the future, I'm not going to continue this long division problem all the way out to the end. When you divide that numerator by the denominator, it creates a new polynomial. And of course, I forgot to write, there's a remainder here, 13/9 over what I divided by. And that polynomial will have the same behavior as this polynomial when we look at what happens when x approaches infinity or negative infinity. What do I mean by that? Well, this divides out to give me a parabola. In fact, it is a parabola opening up. I don't exactly know where it is, and I don't care. I just know that it's some kind of parabola opening up. So if the question is, what happens as x approaches infinity, and we know that it's not honing in on a number, most likely our answer is going to be infinity or negative infinity. And so when you divide this, we are left with 2x squared in the front. That highest power term dictates what this graph looks like. That looks like a parabola, and as x approaches infinity, that's my behavior to the right, this graph is continuing up, which means it is also approaching infinity. So the answer to this question is actually going to be infinity. Now, the faster way to answer that question is actually to divide 6x cubed by 3x. And as soon as you divide those first two terms, you will quickly see that my new resulting polynomial is going to be a parabola, quadratic. You'll see some more examples of this on the next page. All right, so we've talked about how to find horizontal asymptotes and then how to explore the limits algebraically. The next question is actually just finding the asymptotes, and we are not going to do anything algebraically here. So first thing we're going to do is identify the horizontal asymptote, which we just reviewed. So our leading terms have an x squared and an x squared, so the powers are the same. So you are looking for the quotient of their coefficients. So 1 over 1, which would be y equals 1. So that's my horizontal asymptote. For my vertical asymptote, you'll recall, we did this in the beginning of the course, you're going to set your denominator equal to 0. So we would have x squared equals 4, take the square root of both sides, x equals plus or minus 2, don't forget that plus or minus 2. So we have a horizontal asymptote and 2 vertical asymptotes. Let's jump to the next example. My denominator has a greater power than the numerator, so that means I have a horizontal asymptote of 0. Remember your 3 scenarios? So when my denominator has a greater degree, my horizontal asymptote is at 0. And then for my vertical asymptote, again, we're going to set that denominator equal to 0. Now, something to consider that I didn't talk about on the first one is when you set the denominator equal to 0, you're not only finding vertical asymptotes, but also any potential holes or removable discontinuities. So you do want to consider if you could have factored the numerator and denominator. And when you try to factor the numerator, you're looking for factors of -1 that add to -2. The only factors of -1 are -1 and +1, and those terms do not add to -2. So that numerator is not factorable, and that was the same one as on example A, which is why I didn't factor it. I just forgot to mention that to you earlier. So I'm looking at my denominator. I know anything left over in the denominator that creates an undefined function is a vertical asymptote. So I'm going to factor out an x squared, and I'm going to factor this one step further. No, I'm not. I'm not going to factor that one step further. We are ready to solve that. Okay, so when we set x squared equal to 0, we just get x equals 0, and then here we get x equals 1. So we have 2 vertical asymptotes, and we have 1 horizontal asymptote. Okay, if we jump to the next page is talking about finding limits at infinity using the end behavior of a graph. And so when we talk about end behavior, this is also from Algebra 2, we look for the right end behavior first. So if your leading coefficient is positive, your graph approaches infinity. If your leading coefficient is negative, your graph approaches negative infinity. What do I mean by that? Just draw 2 examples. If your leading coefficient of your function is positive, it's the right behavior, so as x approaches infinity, the graph approaches infinity, so your graph is going to head upward. If your leading coefficient is negative, on the right side, the graph will approach negative infinity. The left end behavior is found by looking at what type of power you have. So if your highest exponent is even, the graph approaches the same direction as the right side. A good example of an even function would be like an x squared. And we know with an x squared, think of a parabola, either your graph heads up on both sides or it heads down on both sides. So if you've already identified the right end behavior, then the left side would just match that same behavior. If the exponent is odd, the graph approaches opposite direction. So a really nice, easy example would be like an x cubed. We know an x cubed looks like this. If my graph heads up on the right, it heads down on the left. If my graph heads down on the right, my graph heads up on the left. So if you've already found the right behavior, you would just choose the opposite behavior. So let's look at some examples. So number 5, the limit of x to the 4th as x approaches infinity. Think about what x to the 4th is going to look like visually. My leading coefficient is positive. So to the right, this is approaching infinity. My exponent is even, so it's going to have the same direction as on the right side. So if it's heading up, it is heading up on that side as well. So as x approaches infinity, means the right behavior. This is where x approaches infinity. This is where x approaches negative infinity. So my right behavior would lead to a graph that is approaching infinity. And part B is the question, as x approaches negative infinity, what's happening? Well, it's also approaching infinity. The next example is an x cubed. So on an x cubed, leading coefficient is positive, graph goes up to the right. Exponent is odd, so it goes in the opposite direction on the other side. So as x approaches infinity means the right side behavior, so this graph is heading up, so that is approaching infinity. Part B is as x approaches negative infinity, so that's on the left side. My graph is approaching negative infinity. Look at number 7. Make sure you grab the highest power term. So my highest power term is x to the 5th. Now, once you see other terms, this graph is taking all sorts of curves, but it's the highest power term that is the biggest dictator of what direction your graph is going to take. It has the greatest influence. If I were to substitute an infinity in, that is going to be a much larger value than x to the 4th. So that's why I only have to look at that leading term, the highest power term. So x to the 5th, leading coefficient is positive. This is heading up on the right. Exponent is odd. It's heading down on the left. So as x approaches infinity, that's to the right, my graph is approaching infinity. As x approaches negative infinity, that's my left behavior, my graph is approaching negative infinity. All right, take a look at example number 8. And we've got 3 terms here. You want to make sure you look at the highest power term, which is this one. So it's not always the one that's in the front. So it is a negative coefficient, which means on the right side, my graph is going down. My exponent is odd, so it goes in the opposite direction on the other side. So as x approaches infinity, my y value is approaching negative infinity. And for the same problem, but as x approaches negative infinity, my y value is approaching positive infinity. If you look at example number 9, that is not a polynomial at all, but I wanted you to see a type of function where we can just consider what we know it looks like. So a cosine function starts at pi, and it just continues to cycle. So as x approaches infinity, this does not hone in on a number. So this limit does not exist. And the same thing will be true of a sine function. We know sine starts on the sinusoidal axis or the midline. And as x approaches negative infinity, oh, I just realized this one was also a negative infinity. As x approaches negative infinity, this graph continues to cycle up and down from 1 to negative 1. So that is also a does not exist. Okay, we've got one last thing to look at. If a rational function, so rational functions that don't have horizontal asymptotes, how are we going to find the limit algebraically? Well, I gave you a little sneak peek of that yesterday. So, not yesterday, earlier. So, we saw that on that example number 4, we had no horizontal asymptote, so we long divided. That's what we're going to do here. So, if a rational function does not have a horizontal asymptote, rewrite the function using long division and apply the polynomial and behavior rules. These are the polynomial and behavior rules. So, I see that the numerator has a greater degree than the denominator, so there is no horizontal asymptote. That doesn't mean that doesn't have an end behavior though. So I'm going to long divide. So x to the 6th plus 2x cubed is divided by x squared minus 6x. So you're going to ask yourself, what do I have to multiply x squared by to get x to the 6th? That would be x to the 4th. And I will tell you right now, every single term after that is going to be smaller because you have this written in order, in descending order, based on degree. So I already know that whatever terms are coming up next, they're smaller, so the x to the 4th will tell me what the end behavior looks like. So consider an x to the 4th function. Leading coefficient is positive. This graph goes up on the right. exponent is even, it goes in the same direction on the left side. So as x approaches infinity, this graph, so as x approaches infinity to the right side, this graph approaches infinity. Now, if you wanted to continue multiplying this out and long dividing, that's fine, you can. X to the 4th times x squared is x to the 6th minus 6x to the 5th. And you can continue on and on and on. Make sure you don't add terms that aren't like terms. And you can just see by this example, the very next term, what do you have to multiply x squared by to get 6x to the 5th would be 6x to the 3rd. All of my terms after that are going to get smaller. So I really only need to look at that very first term. Take a look at one last example, example B. So we know that the numerator has a greater degree than the denominator, so I am going to long divide this because there is no horizontal asymptote. So what do I have to multiply x cubed by to get negative x to the 6th, negative x cubed, and everything else is going to be a smaller power. So that tells me what this end behavior is going to look like. So my leading coefficient is negative. This graph is going down on the right. Exponent is odd. This is going in the opposite direction on the left side. Okay, so you've now seen examples where we have found the limits by identifying the horizontal asymptote. We have found the limits by dividing by the highest power term. When it's a polynomial, we have looked at the behavior of the graph and what it visually looks like. And we have also long divided. And that's really all you need to know for this course. But there is one last thing I'm going to show you just for those who are interested. If you're not, you can sign off right now. And it is a technique called using L'Hopital's rule. If you're an IB student, this is only required in HL math. And so what L'Hopital's rule says is sometimes when you are trying to evaluate limits, you have a scenario where you might wind up with a limit of a function over a function. And when you plug your number in, you might get 0 over 0, or you might get infinity over infinity, or any of the negative infinity versions. And so that is called an indeterminate form, 0 over 0 or infinity over infinity. When that is the case, another option to evaluating those limits is instead of finding the limit of f of x over g of x, we can find the limit of the derivative of f of x over the derivative of g of x. So in order to use this, you do have to first prove that you're going to get one of these indeterminate forms. So if you look at example A, if I substituted an infinity in here, I would have infinity plus infinity plus infinity, which would be infinity, over infinity plus infinity minus 9, which is still going to be infinity. So that is definitely an indeterminate form. So what I'm going to do instead is I'm going to find the limit as x approaches infinity of their derivatives. So the derivative would be 24x squared plus 10x plus 3 over 6x squared plus 12x. And if I substitute infinity in, guess what? I still get infinity over infinity. So you keep going. So I'm going to take the derivative of this again. So that would be 48x plus 10 over 12x plus 12. And if I substitute infinity in, I'm going to get infinity over infinity. I'm still looking at that indeterminate form. So I'm going to try one more time. I'm going to take the derivative of the top and the bottom. So the derivative of the top would be 48. The derivative of the bottom would be 12. And finally, I now have a limit I can evaluate. 48 divided by 12 is equal to 4. You will notice that this is an example where we could have evaluated that just by finding the horizontal asymptote. The powers were the same, and my numerator's coefficient is 8, denominator's coefficient is 2, so the quotient of their coefficients is equivalent to 4. So this is just another option. And this type of rule can be very helpful when you have scenarios with no horizontal asymptote. So like an example with letter B, you know that there's no horizontal asymptote there. So if you take the derivative of your numerator and your denominator, let's see if I can squeeze this in here. Actually, let me grab a piece of paper. So in the numerator, when we take the derivative, we're going to get 18x squared minus 2. In the denominator, we would have a 3. And at this point, when you try to substitute an infinity in, you are going to get infinity up on the top, but what I'm seeing is that that is something I can very easily divide out and turn into a polynomial already. So 18x squared divided by 3 would be 6x squared minus 2/3. And if you are finding the limit as x approaches infinity, you can now consider what that looks like as a graph. That is going to look like a parabola that's opening up. My leading coefficient is positive, so my graph, it heads upward on the right side. My exponent is even, it heads upward on the left side. And so I know that my limit here is going to be infinity. Some examples you cannot find algebraically using the methods that we've learned so far. Examples like that would be C or D, where you've got an e to the x, you've got an ln, you've got a sine of x. I'm not going to show those examples because those won't apply to any of our courses this year, but on all of those examples, L'Hopital's rule would be the way to go. Okay, thank you so much for listening. Good luck.